The first speaker is Michele, head of the Project-Based Learning Center at ETH Zurich. And his talk will be about the battery-free, long-range, wireless smart camera for face detection, an accurate benchmark for novel edge AI platforms and milliwatt. Michele, the floor is yours.
Yeah, thank you very much for the introduction and also to having me here. Again, and sorry also for the long title, but you will see that there is a reason, because it's a combination of two works. So as you saw already from the long title, I'm going to present you some things in the range of cameras. So I think maybe many of you can consider it a bit, old. You know very well that camera are everywhere. Miniaturized camera also everywhere. They're used a lot for commercial devices that are really reality. So we can see here narrative. We can see some camera that are on a wearable camera for the cops, and also Forbes say that there is a way to do some kind of smart camera making processing of the images. And what is the reality is that many of these battery operated devices, especially with the camera, today are lasting very few hours, so are not really having a continuous operation, and also most of them are not really smart. So means that they are offloading the processing capabilities, the smart capabilities, to the cloud, rather than having it in an edge device, or in general working with tiny machine learning. So I think also in this case, you know very well, because you are in this community of tiny machine learning, you know that more and more we are talking about pushing IE on and machine learning in general at the edge. There is many advantages on doing it, because we know that we not always have the availability of the network. So we know also with the 3G, 4G, 5G, and further wireless communication, we might don't be covered by the wireless communication, and also the bandwidth at one point will be huge what we require, because we have more and more cameras, we have more and more sensors that stream this information, and especially for latencies, for sure some things that were edge computing, tiny machine learning can help a lot, because we know that the latency achieved by processing the data close to the sensor, it's in order of micro millisecond, rather even with the fast network, we are going straight away in milliseconds or seconds in the worst case, or minutes also. And also for security, privacy, these are some things that where AI can help a lot, especially when we are working with tiny machine learning and also with edge computing, a platform that are able to process this information. So these are some things. This is picture coming from Lattice, where actually I was able to know them in the last summit that we had in San Francisco. So this slide show very well that more we go at the edge means that more we are going closer to the sensors, and there is many advantages, but also every one of you, and from this very nice presentation introduction that we are having from keynote speaker, we know that this can lower the power, but also bring some challenges in having little machine learning running usually in microcontroller. But also here, I'm not saying anything new for you. I'm not surprised that these things you listen at least 10 times in the last 2 days, and so I was thinking how I can impress a bit people in this talk is that let's talk about what might be the next generation IoT, where basically we have some sensors, can be microphone, but also, as you will see in this presentation, can be the camera, where we are going to process the information very close to the sensors with a microcontroller, because we need to be in low power, means we need to be in a range of milliwatt of power. And then if we combine low power design, energy harvesting, that is the technology to get energy from light, like is in this picture, but we can take energy also from vibration, RF power, thermal gradient, and long range communication, we might achieve some very perpetual operation in some things that is truly smart. So we can have, for example, a smart camera that is able to get information from images, detect if there is a particular person in these images, and train the little tiny machine learning inside to these microcontroller, and only if this person, the correct one, can open a gate, for example, that is kilometer of distances, or the application can be very huge. But in general, the main idea here is that with this in mind, we wanted to build a system and an application that combine, including the full integration of the architecture, all these four area. And also from the first talk today, I was very happy to listen that also they believe that the system integration is some things that has to put in count all together. And this you will see in this presentation. This is quite interesting. So as I have only 12 minutes anyway, and also want to talk about the new trend of microcontroller and the benchmark we are going and are going to give today for the first time, but we are soon publishing paper on it. You know very well that microcontrollers today are in the range of milliwatt of power, so very good for energy harvesting, that usually is getting, like for example, this 5 centimeter solar panel is able to get between a few milliwatt of power and 100 milliwatt of power in outdoor. Indoor the situation is worse. So usually we are dealing with processors that are consuming around milliwatt of power. For this reason, the memory, as you know probably very well, is also from the first keynote speaker, in the range of megabyte in the best case, and we have operations that are in the range of mega operation per second or giga operation per second in this power envelope. The new trend is that more and more we are having parallelization and hardware accelerator that are helping these computational capabilities in the same power envelope. This is also some part of my talk. So the idea of this system was also try to have a benchmark on which kind of microcontroller can help this vision of perpetual work. I don't spend too much time in the camera they use, but this is the classical low power iMax used in many similar application scenario. We use also time of file sensor to have a wake up of the system. We have used LoRa for long range communication, and then energy harvesting. So all this information are in a paper that we will see later, so I don't spend too much information on the technical details. But what we also tried, and I think also this is a good overview of microcontrollers today, that we try to compare the most probably 5, there is probably others, so I don't want someone to get offended if I don't include them in this list, but this is what I believe, we believe in our group, that can be the most promising one, especially this very new recent microcontroller from Maxim. Is quite an interesting platform. So here you can see the trend that we pass from a very ultra power efficient microcontroller, single core ARM Cortex-M 4F that I believe everyone of you, to some things that is the first processor with 6 core for Sony. Then there is some custom architecture that have an hardware accelerator and the parallelism with the 2 cores that can process directly the data. There is probably also, this is some things that some of you knows, that there is the parallel RISC-V with 8 core processor PULP that is done in my same institution in ETH Zurich. The new version is the Vega, and there is the commercial version of this PULP that is GAP8. They are also doing GAP9, but we didn't have it, so we tried the GAP8, and then we tried it. Before to pass to this part, I would like to spend 2 words. So we really put in place the full prototype. You will see a little demo later, where there are all information for this. For example, we use actually the worst in terms of energy efficient processor to be in worst case to evaluate the solar panel. But we really test this system in all their part. And as I mentioned, with this processor, you find already a paper with the comparison. You need to wait a bit on, but you can ask more information. The first step, as we already saw, is always build also a tiny machine learning. So we spend a good few months to build a little tiny machine learning, where the main goal was we need to fit these limited resources. We also did a lot of optimization. Actually, this first keynote piece was very interesting because at that time we didn't have it, so we had to do everything by scratch using directly CMC-CNN for ARM Cortex-M4, in general TensorFlow Lite and Micro to really make the quantization for the other platform. But the main goal was really dealing with the little memory and the little computational resources. You can see here that basically there are two convolutional layers with max pooling, and then some two dense network to arrive to the 5 classes that are 5 different phases that we can recognize. It's not face detection, it's really recognition. So this guy actually is the student that is really one that implemented all this version in all this platform, and basically this is phase. So you really have to do the training, all the model to really have at the end some model, tiny model that could work with a 90% accuracy of 5 different phases. We use the Celebrity data set to make also training with many classes, but also we did a data set in our own with our phases done with the people working in the project-based learning center. So the goal was also stay in the little inference time, because we want to be in somehow fast. And we can see here that, of course, we optimize it. So again, also this detail you find in the previous paper, and you will see in the next paper. But an interesting part here is that also with working with the little images, only 30 for 40, the accuracy was not lost so much. And also going from the floating point to from quantized 8-bit quantization with all integer, we were not losing so much. So at the end, we were able to really implement. We were happy with this network, and we were really going to implement this final network. Why we implement this final network? First of all, to have this prototype ready to show that combining long range, energy harvesting, ultra low power microcontroller, it's possible to achieve this zero battery-less camera that work forever, doing some things important. It's not only a single camera that sends some picture away, but is really detecting some different person eventually take an action. And also this probably is the most important part that people like you are interested in, to really have a benchmarking in a real network that we really used for a specific application. This is start to be the interesting part. You can see that the Apollo 3, thanks to the technology from the nearest threshold transistor technology they are using for making the ARM Cortex-M4, is the best in power. And actually, the new Maxim is the worst in power per megahertz, of course. We're talking power per megahertz. And you can see here the overall power that, except the case of the X-core, all are all in the X-core is in the range of 100 milliwatt of power. The other are below 100 milliwatt of power. So this is the case of 4 milliwatt of power. So what is the best in the power efficiency? It's actually still very good, but not the best in terms of energy per inference. So, and actually the worst in terms of power per megahertz is actually the best in energy efficiency. How this is possible? So, you probably has already the answer to the question. It's possible because actually we are using, in the case of the Maxi, they are using, so we are exploiting the very good design that they did. They are using an hardware accelerator able to reduce significantly the time for inference. Even running only 50 megahertz, this processor is able to deal with similar, very novel. These are both very novel, so they are using. So we are really comparable here in terms of technology. We are using very novel processor running much faster. First, I have to say that here, as you can see here, we are not exploiting the hardware accelerator here for many reasons. I don't go in details of the reason, but here we are using only the parallelism. So this number is probably will increase if we are using only the hardware accelerator. But the Maxim is able to get more than 100 meg per cycle. This was very impressive. We also contacted Maxim to be sure that we were doing the things right, and actually they confirmed that this Maxim can give this information. You can see also the effect of the not having cache, like in the case of the Sony Express Sense, that bring the single core quite inefficiency, but still with the 6 core is getting advantages with a normal ARM Cortex-M4. But you can see that the trend of having hardware accelerator and parallel architecture pay off, because you can see that they are significantly better. We also did a simulation with a simulator from ARM ARM M55 just to see where we are, and you can see that there is no chance. Still, it's it's much better having parallel architecture, and hardware accelerator is some things that it's still winning. And again, I don't want to spend too much time. Why we are interested on it? Because of course you can imagine that if we are having less inference energy for inference, this benefit the battery lifetime, but also benefit the fact that with a little energy coming from indoor light, we can have a perpetual work of the camera to see before, only with 100 lux. So I don't have too much time. Again, you have some things. So I want to also show that this camera is really working. I don't know if you are listening it, but I talk on it. Yeah, I don't know if you are listening it. So you are really tapping the wireless sensor node. Can you really stay in it?
No, unfortunately.
Okay, so I can tell you what is happening. So basically, it's really attached with tape this sensor node, and you can see that this was able to recognize the student. This is a student that did all the hardware software design, and sending with LoRa in the gateway this information here that this is stored in database, but means that this really recognize the student, like Marco Giordano is his name, and then it could activate anything here. And no battery, no other things. Is really working indoor with this little light here, and this is more than enough for having here. So I want to conclude, and then we really show the hardware software design of a battery-less long-range wireless camera, and this accurate, interesting benchmarking to show that actually new trend of the sensor is benefit the system integration, and the people like me that are more working in embedded systems and application to really make some things that it's even is overperforming the inference time energy that we were not thinking even 1 year ago that was possible. So I conclude here, and I'm open for questions if there is time. I put also some acknowledgement for the people that help from the companies that help to make this benchmarking in the more fair way that we could do. Thank you very much.
Thank you, Michele, for the very interesting presentation. I don't see a question in the Q&A. In the meantime, maybe I can ask a question or two. So can you please clarify, does the camera also do the detection part, or is it just working on the cropped face?
Actually, so I was a bit too fast because I wanted to explain many things. But the idea is that so we are not cropped. So the camera we are using this little image here, and so basically we are setting up the camera to get directed 40 by 30 pixel. So we are working directly with so we are not taking this red block here, but we are really I will just put for clarification that we are going to check the information here, but we are working basically with this image that you can see down here. So we are working directly for 40 by 30 pixel where is included the camera. So also we were very surprised of the fact that we were not losing so much in terms of accuracy, going from 240 by 320 to 30 by 40. Okay. And then all the processing is done on the microcontroller.
Okay, thank you. There are a couple of questions in the Q&A, very fast. The first one is by Daniel Guevara, if you have a version with Sigfox communication. And the second is by Weir1, if you have a processor benchmark results published.
These at the moment I would say I feel quite confident with these results. So I start from here. So, but I would like to, before to publish, do another sanity check. So you consider that, for example, for Xmos, for Max, for the PULP, we are working close to the person that design the hardware. We are doing the software and the benchmarking part. I think the plan is publishing it. So I think very soon, when we have all the cross check that all the numbers are correct, we are going to publish. And so I think meantime I can give this information, but I think we work a lot on it, so I'm quite confident these are very similar. Of course, there's some things that need to be clarified for example, the hardware accelerator we need to use, so this number could be reused. So we are going to publish. For Sigfox, we don't have at the moment a version with Sigfox, but this can be done. So I think at the moment this is done with normal SPI communication, and we can replace the LoRa part with the Sigfox without any problem, and this can be done in future, but it's not ready in our system.
Okay, thank you, Michele.
This would not be made possible without our sponsors, whom I would like to once again express our gratitude, starting by premier sponsor Newton.ai. Thank you guys so much. The executive sponsors, which involve ARM, Edge Impulse, Qualcomm AI, and Sentient. The platinum sponsors, which involve Infineon, Reality AI, the gold sponsors, which involved Latent AI, SensiML, and last but not least, our silver sponsors, which involve EMSA, Greenwave, Kixo, Imagimop, HOTC, Seed Studio, and ST Microelectronics. Thank you, everybody. See you all tomorrow with more exciting features.